Hi, my name is Shanawaz. Let us recall what we did in last lecture. So we had the open sets UI, which contain elements of the form, say A node up to AN. So they are the points in the projective n space with the coordinate AI non-zero. So then we can define the map phi from UI to AN, where this point, the point A naught up to AN. So this is carried to the point A naught by AI up to AI by AI, but this term is omitted, and up to AN by AI. So in last lecture we proved that this map is an isomorphism. So by isomorphism here we mean the map phi I from UI to AN is a morphism with inverse phi I inverse, which is a map from AN to UI, while the element say we had a point, let us call this point A, um, let us call this point A1 up, let us call this 1 here, and let us write a hat here. So this is up to AN. So this is carried to the point uh, A and A1 up to AN. So this map is also a morphism. So we have phi I whose inverse is also a morphism. So that means both phi I and phi I inverse are continuous. So with respect to Zariski topology, this means that phi I is a homeomorphism. So that means the set UI, this is homeomorphic to the affine n space. So now in particular, we want to prove that every locally closed subvariety of this affine n space is isomorphic to a quasi-projective variety. So this is what we want to prove here. So, but before proving this, we have a remark to make. So let us write this down. So one can note that. So this is true for any I. So this is in particular, this is true for I is equal to 0 as well. So since phi 0 from u0 to an, so since this is an isomorphism, so we can I mean we can identify, so we can identify this point. So one can note here we have drawn a curve over here, so that means this term is not there, so one cannot write, one can omit this term. So this is up to an. So we can identify this point, the point a1 up to an. So before it was a0, and here the term a I cap is being removed. So we can identify this point which is in affine n space. So we can identify this point with, so we have one here. So we can identify this point with the class a1, sorry, because here I is 0, so 1 is at the first place, 1 a1 up to an. So this is in the projective n space. So, or this is in particular, this is a point in u0 which is contained inside pn. So with this identification we can assume that an is a subset of pn. We can embed an into pn. So thus uh, an is a subset of Pn. Um, this actually means that An can be identified by a subset of Pn, which is A0 itself. So if this is the case, that means the Zariski topology on An is actually the inducer topology of the Zariski topology on Pn. So hence the Zariski topology on An is the inducer topology, I mean a subspace topology, inducer topology of the Zariski topology on the projective n space, I mean Pn. So if we consider say x, so if we consider this x a closed set, so then we can write x as the x bar intersection affine n space, where this x bar is a closure of x in Pn. So where x bar is the closure of x in Pn, because An, we can think of An as a subset of Pn. So now with this identification, the closure subvariety, so with this identification, the closed subvariety x, which is called the closure of x in An, sorry, in Pn intersection An. So this is an open subvariety. So this is an open subvariety of the closure of x, and hence a quasi-projective variety. So we want to prove actually the locally closed subvarieties of An are isomorphic to quasi-projective varieties. So let us prove this. So this is the consequence of the previous result. So that means it states that every variety is isomorphic to a quasi-projective variety. Let us prove this. So let us assume, so we have a proof. So let us assume that x is a variety. So let x be a variety. So if x is locally closed subvariety in Pn, then by definition x is quasi-projective variety, and hence there is nothing to prove. So if x is locally closed subvariety in Pn, then by definition X is a quasi-projective variety. So this follows from this fact here. We can think X to be an open cell variety of X bar, which means it's a quasi-projective variety. So thus in this case there is nothing to prove. So there is nothing to prove. Now assume that the X is an affine locally closed variety. Now if this is the case, so since we know that the morphism P naught from U0 to AN, so we know this is an isomorphism. So if this is an isomorphism, this means this is also a homeomorphism. So therefore, if we look at the inverse image of X in AN, let us call that Y. So Y is the inverse image under phi 0 of X. So this is then locally closed in U0. So then the set Y, which is the inverse image of X under phi 0, is locally closed in U0. Now, this being locally closed in U0 means it's locally closed in Pn, because U0 U0 is a subset of Pn. So and thus in Pn as well. So this implies Y is a quasi-projective variety. So this implies Y is a quasi-projective variety. So one can note here that we have to prove X is a quasi-projective variety. So it suffices to prove that the sets Y and X, they are isomorphic. So, but note that if we restrict phi to Y, then this phi will be a map from Y to X. So this is an isomorphism. Because this phi is actually the restriction of this map phi naught, which is given to be a morphism, an isomorphism. So this is an isomorphism as the restriction of an isomorphism. So this means that this y and this x is also a quasi-projective variety, because these sets, I mean, the set y and x, they are isomorphic. So this proves the result. Now we want to show that every variety has an open cover by affine varieties. So this will, this will allow us to reduce many problems to the case of affine varieties. So we have this theorem here, which states that every variety is an open cover, I mean every variety has an open cover by affine varieties. But one should keep in mind that every variety is as we seen in this result here, that every variety is isomorphic to a quasi-projective variety, which uh, also implies that all varieties are quasi-projective. So that is what we are going to use in this result. So let us prove this. So let us pick a quasi-projective variety in Pn. So let X contained in Pn be a quasi-projective variety. So one should keep in mind here that every variety being isomorphic to quasi-projective variety, so we only need to care about the quasi-projective varieties. So that is why we assume here that X is a quasi-projective variety, because if X is any other variety, then the variety is going to be isomorphic to a quasi-projective variety. So let us assume that X is a quasi-projective variety. So we have to prove that we can cover this X by affine varieties. So note that the open sets UI where UI is the set of all points in the projective space with the ith coordinate non-zero. So we know this covers Pn. So this is an open cover of Pn. So if this is the case, therefore uh, now X being a subset of Pn, and this implies the collection UI intersection X. This is an open cover of X. So one can note here that is X is a quasi-projective variety, hence X is open, and these UIs they are also open. Now since these UIs, since they cover the whole projective space, that means this collection here, this covers X. So, so one can see here that for any so one should note here that, so let us go to the next page. So one can see that for any I, the variety X intersection UI. So this is isomorphic to a locally closed subvariety of AN, because we have proved this. So this is isomorphic to a locally closed subvariety uh, of AN. Now using this fact, we can assume that this X is contained in AN is locally closed subvariety. So therefore That means this x intersection ui, this is isomorphic to some, say yi, where y is locally closed subvariety of an. Now since these x intersection u as they cover x, so we can assume that uh, this x is actually inside an, uh, which is a locally closed subvariety. So that means now this x being a locally closed subvariety, this means this x is actually the complement of a closed set in a closed subvariety of x. So that is this x is actually the complement of a closed set z in the closed set y. So with y and z, they are closed subsets of an. So let us pick any point in x. So let p be any point in x. So actually, it is enough to prove that there is an open, I mean, affine open subset uh, of x containing p. So I mean, uh, we have a slide. So actually, it is enough to find, enough to show that uh, there is open, there is an affine open subset, open subset of x containing p. So here what I mean that since p is inside x, so now to show this x is we have to actually prove that this x can be covered by affine varieties. So to prove it, what we are going to do, we are going to pick some any arbitrary point, say p in x. Now by choosing the point p in x, now it suffices to show that there is an affine neighborhood, open neighborhood p of p in x. Now we have to exhibit that neighborhood. So one can note here, since this p is inside x, so that means p is inside y but not in z. So since p belongs to x, which is equal to y minus z, that means, so then there is a polynomial in the ideal of x which does not vanish at p. So then there exists say a polynomial say f in the ideal of z, which is contained in the polynomial ring x1 up to xn, such that f ceases to be 0 at p. I mean, f of p is different from 0. So that means, so if this f uh, does not vanish at some point of y, that means the y is not contained inside 0 set of f. So that is y is not contained inside the set, I mean the vanishing set of the polynomial f, because there is some point p in y where the polynomial f does not vanish. So if this y is not contained in zero set of f, so therefore the principal open, I mean, so therefore uh, therefore the principal open, I mean y sub f, so defined by f, so this makes sense. So one should remember the definition of principal open uh, defined by some polynomial. So why this makes sense? Because of this condition here, y is not contained in the zeros of f. So that means this y sub f, which is a principal open defined by f. So this makes sense. So one can note that this we have proved that this principal open is actually an affine variety. So note that y sub f, which is by definition equal to the y minus the zero set of f. So this is an affine variety. So note that y sub f is an affine variety. This is also open because z of f is closed. So the complement of closed set is open set. So this is an affine variety which is also open because it is the complement of a closed set, because this is the affine algebraic set. So thus what we proved, thus we proved that this p is in y sub f because this p does not belong to the zero set of f. So if this is not in the zero set of f, so it has to be inside y. So that means we proved that there is some affine open subset which contains p and is contained in x. I mean uh, we succeed in proving that there is an affine open neighborhood of p contained in x. So hence y sub f is an affine, so this is an affine open neighborhood of p, open neighborhood of p in x. So this proves our claim. So one should I mean we proved in one of the previous lectures that a morphism p phi from affine variety, say from x to y, where y is contained in a n. So this is a morphism if and only if this phi is given by the regular functions of n tuple of regular functions on x. So i.e. this phi is given by say h1 up to hn, where these hi's, they are the regular functions on x. Now what we want to prove here, so we want to give a simple description of morphisms to affine varieties. I mean we have to we want to characterize the morphisms to affine to projective varieties. So for that we have the following result. So this results characterize the morphisms um, to the projective varieties. So let X contain in Pm and Y contain in Pn. Suppose they are quasi quasi-projective varieties. So again, one should keep this in mind why we are assuming X and Y to be quasi-projective varieties, because we just proved that all the varieties are quasi-projective varieties. I mean, any variety is isomorph to a quasi-projective variety. So let's consider, so let phi from X to Y be a map. Then the following are equivalent. The first item is phi is a morphism. The second item is phi is locally given by regular functions. That is, for all p inside X, there exists, so there exists a neighborhood, an open neighborhood, say U inside X. So there is an open neighborhood U inside X of P, and the regular functions, say h0 up to hn. So these are the regular functions on U. So they are the regular functions on U with no common zeros, with no common zero in U, such that this phi is given by, I mean, such that phi of Q is same as h0 of Q up to hn of Q for all Q inside U. So that means this phi is given by this function h0 up to hn. Now we have the third item. Phi is locally a polynomial map. Phi is locally a polynomial map. Note that the locally means that this thing, I mean, for the point P, we have an open neighborhood U such that this hypothesis is true. So phi is locally a polynomial map. So that is, for all points P inside X, there exists an open neighborhood U of P, and the polynomial, say f naught up to fn inside the polynomial ring in n plus 1 variables. which are homogeneous of same degree with no common zeros on U, which are homogeneous of same degree and no common zero in U, such that this phi is given by the n tuple, I mean f0 of q, I mean this n plus 1 tuple, f n of q for all q inside u. So this is same as to say this phi is given by this n tuple, n plus 1 tuple up to f n. So let us prove this. So first implies second. We are going to assume that phi is a morphism. So let phi from x to Pn be a morphism. So we have to prove that this phi is locally given by regular functions which have no common zero in U. So let P be any point in X. So since Ui, so since this is an open cover of Pn, so this Pn is covered by these Ui's. That means this phi of P belongs to some Ui. So then phi of P belongs to some Ui for some I. Now without loss of generality, we may assume that I is 0. So without the loss of generality, we may assume that this I is 0. So this is for the notation, I mean for the simplicity. Now note that since phi 0 from, I mean phi I from ui to an, which we know, I mean we know this map. So this is, uh, let us mention this map here. So given as, so this phi I takes the point inside the ui which is of the form a naught up to an. So it maps this point to the n tuple a0 over ai up to ai over ai. So we have a hat here to emphasize that this point is not there, to an mod ai. So we have proved that this map is an isomorphism. So this is an isomorphism. So we may identify u0 with an. So we can identify u0 with the affine n space. So thus phi of p, which we assumed here that this is, so we assumed that phi of p here, this is in ui, but we are assuming that this I is equal to 0. So that means we can assume, I mean we can conclude that this phi I is a point inside an. So thus we have reduced this case to the, I mean to the affine case. Now the things uh, gets easier. Now let us pick some open neighborhood. Say u of phi of p. So let u be uh, so let u be an open neighborhood of p with phi of u contained inside an. So if this is the case, then the restricted map, then the restriction phi to u, which is a map from u to phi of u, to an. So this is a morphism. So if this is a morphism, thus in affine case, we can write this restriction to u. So this is given by an n tuple of regular functions. So where hi's are regular on u for all I equal to 1 up to n. But so we know we can identify this point h1 up to hn. So we can identify this point in an with the point. So this is identified. So this is identified with the point 1 h1 up to hn in the projective n space Pn, and hence this restriction map phi to u, this is given by this map h1 up to hn. Thus phi is locally given by regular functions. So where these hi's, they are regular on u. So thus phi is given by, so this phi is given locally by regular functions. So this proves the first item, uh, the case first implies second. Now to prove the second item, let us assume that second is true. So assume that phi is given locally by regular functions. So this means uh, so that is for any point p inside x. So that is for any point p inside x, there exists an open neighborhood, say u inside x of p, such that this p is given by regular functions, say h naught q up to h n q. So this is true for all q inside u with where these hi's where hi's are regular on U with no zero, with no common zero in U. Now we have to prove that this phi is also given by also locally given by polynomial. So for that we make U smaller if necessary. So by making U possibly smaller, we can assume that this hi is given by fi over gi, with these fi and gi to be homogeneous polynomials. So they are the homogeneous polynomials in n plus 1 variables, and with same degree. And gi non-zero on U. Now that is, we can write this phi to be the function given as f0 over g0, f1 over g1 up to fn over gn. So for I equal to 0 up to n, we put, so let us put li to be the polynomial fi times the polynomial g0 dot g1. So we have gi hat here dot gn. So one can note here we are removing gi here, degree of gi, and that is what we are subtracting. But we at the same time we are adding the degree of fi. Since the degrees of fi and gi are same, so these li's they remain homogeneous and of same degree for all I. So then li are homogeneous. So these li's are homogeneous polynomials of same degree. Also, now since these gi's they do not have a common zero inside U, that means these li's also, so also the polynomials li, where I is from 0 up to n, so they do not have common zero on U. So they do not have common zero in U. So we can write, this phi as the by the polynomials L0, L1 up to Ln. So actually we are taking the LCM of these denominators and we are multiplying by the LCM. So we get these polynomials Li. So that means this phi is locally given by these polynomials, and these polynomials they do not have a common zero on U. So finally we have to prove third implies first. So assume that uh, in a neighborhood U of P, we have, I mean, this P is locally given as the, given by the polynomials. It is given by the polynomials h0 up to hn, where hi's are homogeneous polynomials of same degree with no common zero on U. So we have to show that this phi is homomorphism. Now to prove phi is homomorphism, it suffices to prove it is a morphism when we restrict this p to u, because we know if we have, say, we have varieties, say x and y, and phi is a map between, this case is like this. So if phi is a morphism from x to y, and suppose we have an open cover, say ui, so we have an open cover ui's of x such that phi restricted to each ui, which is a map from ui to y. So if this is a morphism, then this phi is a morphism. So this is the result that we have proved in one of the previous lectures. So here it suffices to prove that this phi is a morphism when we restrict this phi to u. So so we want to show phi restricted to u uh, is a morphism. So now by making u smaller, by making u smaller, we may assume we may assume one of the hi's, say we may assume one of the hi's, say let us suppose h0 is nowhere vanishing on u. So this is nowhere vanishing on u. H0 does not vanish at any point on u. So then if we put this little hi to be the polynomial hi over h0, so then this hi is a regular function over u. So it's a regular function over u. So therefore if we restrict phi to u, so if we so this will be equal to the map 1. So actually we are dividing each hi by h0, so we get the map 1 h1 over h1 up to hn. So we can identify this element by h1 up to hn. So this is a map from u to an. So this is a morphism. This is a morphism. Thus phi is a morphism. Thus phi is a morphism in a neighborhood of every point, in a neighborhood of every point. So thus it is a morphism. Thus phi is a morphism. So this proves the result.